Welcome to the problem walkthrough for LeetCode number 221, Maximal Square. In this problem, we'll explore how to find the largest square containing only ones in a binary matrix. We'll cover multiple approaches, analyze their time and space complexities, and discuss the optimal solution. Let's dive in. In this problem, you are given a binary matrix, which is a grid of dimensions mxn where each cell contains either a 0 or a 1. Your task is to identify the largest square that can be formed using only ones in the matrix and then return its area. The key challenge here is to determine the maximum square submatrix of ones and compute its area, which is the square of its side length. The input to the problem is the binary matrix itself, represented as a 2D list or array, and the output is a single integer representing the area of this largest square. For example, consider this matrix. Here, we have a 4x5 grid, and we need to find the largest square that can consist entirely of ones. The output for this input is 4. This is because the largest square that can be formed has a side length of 2, and the area of a square is calculated as the side length squared, giving us 2 multiplied by 2, which equals 4. Now, let's look at another example. In this matrix, we have a 2x2 grid. The largest square containing only ones has a side length of 1, so its area is 1 multiplied by 1, which is 1. Similarly, in the third example, we have a single element matrix containing only 0. Here, there are no ones, so it's not possible to form any square of ones. The area of the largest square in this case is simply 0. Finally, let's discuss the constraints and edge cases. The number of rows and columns in the matrix, M and N, can range from 1 to 300. Each cell in the matrix will always contain either 0 or 1. Edge cases include situations where the matrix contains only zeros, in which case the output should be 0, or only ones, where the area would be the entire size of the matrix. If the matrix has only one row or one column, the solution depends on the presence of any one. For very large matrices, such as 300 by 300, the solution must be efficient to avoid exceeding computational time limits. To start, let's consider the brute force approach. The basic intuition here is to treat each one in the matrix as a potential top left corner of a square. For every such cell, we systematically attempt to form squares of increasing size, ensuring that all the cells within the square are also 1. The process involves iterating through every cell in the matrix and then expanding outward from each one to verify larger squares. While this approach is conceptually simple, it has significant limitations. The time complexity is O, open parenthesis m times n close parenthesis squared, which becomes impractical for large matrices due to the nested loops and repeated calculations. On the bright side, it doesn't require extra memory, with a space complexity of O, 1. However, the redundancy in recalculating overlapping areas makes this approach inefficient and unsuitable for competitive programming or large-scale input sizes. Now, a more efficient solution builds on dynamic programming. The key insight here is to track the largest square ending at each cell. If a cell contains 1, the size of the maximal square at that position can be derived from 3 neighbors, the top, left, and top left diagonal cells. Specifically, the size of the square at any cell, I, j, is determined using the recurrence relation, dp, I, j, equals the minimum of the values at dp, I1, j, dp, I, j1, and dp, I1, j1, plus 1. This ensures that the square is as large as possible while remaining valid. To implement, we create a dp table matching the matrix dimensions, initialize it to zeros, and then iterate through each cell, updating the dp table based on this recurrence. By keeping track of the maximum value in the dp table, we can calculate the area of the largest square by simply squaring that maximum value. The dynamic programming approach significantly reduces redundant calculations, improving time complexity to O, m*n, since each cell is processed exactly once. However, this comes at the cost of additional memory, as the dp table requires O, m*n, space. To address this, we can use a space-optimized variation that only stores the current and previous rows of the dp table, reducing the space complexity to O, n. This rolling array technique trades off simplicity for efficiency, as it slightly complicates the implementation. While both the standard and space-optimized dp approaches run in O, m*n, time, the latter is particularly useful when memory is a critical constraint, such as in environments with limited resources or very large matrices. Ultimately, the dynamic programming approach strikes the best balance between simplicity and efficiency. It eliminates the redundant recalculations of the brute force method while remaining straightforward to implement and debug. Although the space-optimized variation offers reduced memory usage, the added complexity isn't necessary unless memory is explicitly limited. The DP approach is scalable, running efficiently even for large matrices, and provides a clear and systematic pathway for solving the problem. While the brute force approach may be easier to conceptualize, its inefficiency makes it unsuitable for practical use. Overall, the standard dynamic programming strategy stands out as the ideal choice, balancing clarity, maintainability, and performance while leaving room for further optimization if needed. To solve the problem of finding the largest square of ones in a binary matrix, we need to determine the side length of the largest possible square entirely made up of ones, and then compute its area. For example, if we have a matrix filled with zeros and ones, we aim to identify the largest square submatrix consisting solely of ones. The brute force approach begins with a simple intuition: treat everyone in the matrix as a potential top left corner of a square. Starting from each of these positions, we attempt to expand the square incrementally while ensuring that all cells within the square remain valid, meaning they must also be 1. To implement this, we first initialize variables, including max_size to track the side length of the largest square found so far. Then, we loop through all rows and columns of the matrix to identify potential starting points. If a cell contains a 1, we treat it as a candidate and begin expanding the square from that point, verifying the validity of all cells within the expanded region step by step. When expanding the square, we start with the smallest possible size, which is just the cell itself, and then incrementally increase the square's size by checking additional rows and columns. For each new size, we confirm that all cells in the rightmost column and bottom row of the square are also 1. If this condition is satisfied, we continue expanding, otherwise, we stop. At each valid expansion, we update max_size to reflect the largest square found so far. If a square exceeds the matrix boundaries or encounters a 0, the expansion halts. Finally, once all potential squares in the matrix have been evaluated, the area of the largest square is calculated as max_size** max_size. However, this brute force approach is inefficient due to its redundancy. Many cells are checked multiple times when evaluating overlapping squares. This results in a worst-case complexity of n³ for an nxm matrix, making it impractical for larger grids. Additionally, certain edge cases must be handled, such as matrices containing only zeros, which should return an area of 0, or very small matrices, such as 1x1 grids, where we need to manage both 0 and 1 inputs correctly. To address the inefficiencies of the brute force approach, we turn to dynamic programming. The input remains a 2D matrix, which allows us to access individual cells in constant time. We also maintain a variable to store the size of the largest square found, ensuring we don't have to recompute results. The dynamic programming technique optimizes the solution by breaking the problem into subproblems and storing their results in a DP table. The key insight here is that the size of the largest square ending at a given cell depends on the smallest square sizes ending at its top, left, and top left neighbors. Specifically, the transition relation is dp I j equals min dp I1 j dp I j1 dp I1 j1 plus 1, provided the current cell contains a 1. This eliminates the need to repeatedly verify overlapping regions, significantly reducing redundant calculations. Furthermore, space optimization can be applied by reducing the 2D DP table to a 1D array, since we only need information from the previous row at any given time. In terms of complexity, the dynamic programming approach reduces the time complexity to O(n*), as each cell is processed once, and the space complexity can range from O(n*) to O(n), depending on the implementation. Let's walk through an example to see the dynamic programming approach in action. Consider the input matrix 1, 1, 1, 1, 1, 0, 1, 1, 1. We begin at cell 0, 0, and calculate the size of the largest square ending at each cell using the DP relation. For instance, starting with the top left corner, we find that the square expands to size 2 by checking all relevant cells. However, the presence of a 0 at cell 1, 2 prevents further expansion. As we proceed through the matrix, we discover that the largest square has a side length of 2, corresponding to an area of 4. This value is computed as max_size asterisk max_size, which we return as the final output. By following this process, we efficiently calculate the solution while avoiding the redundancy of the brute force approach. This solution implements a dynamic programming approach to solve the maximal square problem efficiently. First, we check if the input matrix is empty or invalid, returning 0 if true. Then, we initialize the DP table, dynamic programming table, as a 2D list of zeros, with the same dimensions as the input matrix, to store the side lengths of squares ending at each cell. We also declare max_side to track the maximum square side length found. The algorithm iterates through each cell in the matrix. If the current cell contains a 1, we calculate the value of dp, I, j. For cells in the first row or column, dp, I, j is simply 1, as no larger square can end there. For other cells, we determine the side length by taking the minimum value among the top, dp, I1, j, left, dp, I, j1, and top left diagonal, dp, I1, j1, neighbors, and then adding 1. This ensures that the square is contiguous and composed entirely of ones. During the iteration, we continuously update max_side to keep track of the largest square encountered. Finally, after the loop completes, we return the area of the maximal square as max_side asterisk max_side. This algorithm runs in O, m asterisk n, time, where m and n are the number of rows and columns in the matrix, respectively, and uses O, m asterisk n, space for the DP table. This makes it an efficient and robust solution for the problem. Here, we start by importing necessary packages and defining the solution class along with the maximal square method. The method takes a 2D character array matrix as input, representing the binary grid. We first handle edge cases by checking if the matrix is null, empty, or has no columns. If any of these conditions are true, we return 0 since no square can be formed. Next, we initialize some variables, rows and calls to store the dimensions of the matrix, a 2D array dp to track the size of the largest square ending at each cell, and max_side to keep track of the largest side length encountered so far. We then use a nested loop to iterate over each cell in the matrix. If the current cell contains 1, we calculate the size of the square that can end at that cell. For cells in the first row or column, the value in dp is set to 1 since no larger square can be formed. For other cells, we calculate dp, I, j, as the minimum of the values above, to the left, and diagonally up left in the dp array, plus 1. This ensures that we only form squares where all contributing sides consist of ones. Finally, we update max_side to reflect the largest square side length found so far. After completing the nested loop, we calculate the area of the largest square by squaring the max_side value and return the result. Wrapping up the method, we close the class definition. This implementation efficiently uses dynamic programming to compute the maximal square in O, m asterisk n, time, where m and n are the dimensions of the matrix, while maintaining a space complexity of O, m asterisk n, due to the DP array. This ensures that the solution is both optimal and easy to understand while handling all possible edge cases effectively. In this problem, our goal is to find the largest square composed entirely of 1s in a given binary matrix and return its area. To solve this efficiently, we will use dynamic programming. Let's start with an example matrix. The input matrix has dimensions 4 rows by 5 columns. To keep track of the largest square we can form, we initialize a DP table of the same size, filled with zeros. We also maintain a variable max_side to store the side length of the largest square found so far, starting at 0. The plan is to iterate through each cell in the matrix and calculate the size of the largest square ending at that cell using a dynamic programming relation. For cells in the first row or column, the DP value is simply 1 if the matrix has a 1 in that position. For the rest of the cells, we compute the DP value based on the values from adjacent cells in the DP table. Now, let's process the first few cells of the matrix step by step. At I equals 0, j equals 0, the value in the matrix is 1. Since this is in the first row, we set dp 0, 0 to 1 and update max_side to 1. Next, at I equals 0, j equals 1, the value in the matrix is 0, so we leave dp 0, 1 as 0. At I equals 0, j equals 2, the value is 1, so we set dp 0, 2 to 1, and max_side remains 1. We continue this process for the rest of the first row. Now, moving to I equals 1, j equals 2, the value in the matrix is 1. Here, we compute the dp value as the minimum of dp 0, 2, dp 1, 1, and dp 0, 1, plus 1. This results in dp 1, 2 being 1. Similarly, at I equals 2, j equals 2, the value is 1, and the computation gives dp 2, 2 as 2, meaning we can form a square of side 2 ending at this position. We update max_side to 2. After processing the entire matrix, the largest square has a side length of 2, and its area is 4. The final dp table shows the progression of values as we processed the matrix. To better understand edge cases, let's look at a matrix that contains only zeros. Here, since there are no 1s, every dp value remains 0, and max_side does not change. The result is an area of 0. Next, consider a single-row matrix where all elements are 1. Since there is only one row, each cell can only form a square of side length 1. As we iterate through the row, we set each dp value to 1, and max_side remains 1 throughout. This means the largest square has an area of 1. These examples illustrate how the algorithm handles matrices of different structures, ensuring the solution is robust even for edge cases. In the single-row example, we initialized the dp table as a single row with all zeros and set max_side to 0. As we processed each column, we updated the dp values based on whether the matrix had a 1 in that position. For I equals 0, j equals 0, dp 0, 0 became 1, and max_side was updated to 1. Similarly, for I equals 0, j equals 1, dp 0, 1 was set to 1, and max_side stayed 1. This pattern continued for the rest of the row, resulting in a dp table filled with 1s. The largest square has an area of 1. Key observations from all these cases include the fact that each dp, I, j, represents the side length of the largest square ending at I, j. The recurrence relation ensures that we only consider valid square extensions by using the minimum of adjacent dp values. Finally, the time complexity of this approach is O, rows asterisk calls, and the space complexity is also O, rows asterisk calls, though it can be optimized to O, calls, by using a rolling array for the dp table. Here, the time complexity of our solution is derived from the nested loops that iterate through the matrix. The outer loop runs through each row, and since there are rows, this loop iterates rows times. For each row, the inner loop goes through its columns, which means it iterates calls times per row. Multiplying these together gives us rows asterisk calls total iterations, which corresponds to the total number of cells in the matrix. Within each iteration, the operations performed are constant time. Checking if the current cell contains a 1, retrieving values from the dp array, and calculating the minimum of 3 numbers all require O1 time. Since these operations are performed for each of the rows asterisk calls cells, the overall time complexity is O, rows asterisk calls. This efficient scaling ensures we process the matrix in a time proportional to its size. Now, let's explore the space complexity of the dynamic programming solution, which is primarily determined by the dp array. This array is a 2D list with dimensions rows x calls, where each cell holds the size of the largest square ending at that position. As a result, the space required for the dp array is O, rows asterisk calls. Apart from this, we use a few additional variables, such as max_side, which take up constant space, or O1. The dominant factor in our space usage remains the dp array, giving us an overall space complexity of O, rows asterisk calls. Comparing this to a brute force approach, where every possible submatrix would be checked to see if all values are 1, the naive method would have a time complexity of O, rows asterisk calls, 2, because it would involve iterating over all submatrices and validating each one. Dynamic programming avoids redundant computations by storing results, reducing the time complexity to O, rows asterisk calls, while maintaining manageable space requirements. To better understand the performance, we can analyze the algorithm under different scenarios. In the best case, where the matrix contains no ones, the algorithm still scans all cells, resulting in a time complexity of O, rows asterisk calls. In the worst case, where every cell contains a 1, the algorithm fully computes values for all cells, but the time complexity remains O, rows asterisk calls, since each cell is processed only once. On average, the algorithm handles partial submatrices, but the asymptotic complexity doesn't change, it's still O, rows asterisk cols. Mathematically, if we let n represent the total number of cells, which equals rows asterisk cols, each cell is processed exactly once with constant time operations. Therefore, the total work is proportional to n, confirming the time complexity is O, n, or O, rows asterisk cols. Similarly, the space complexity stems from the DP array, which also requires O, n, or O, rows asterisk cols, space, as it scales directly with the number of cells in the matrix. In summary, the dynamic programming approach achieves both a time complexity and a space complexity of O, rows asterisk cols, making it significantly more efficient than the brute force method, which has a time complexity of O, rows asterisk cols, caret 2. By leveraging the DP array, we avoid redundant computations and store intermediate results, ensuring optimal performance for processing the matrix. This efficiency highlights the strength of dynamic programming in solving problems that involve overlapping subproblems and optimal substructure, such as finding the maximal square in a binary matrix. When tackling the maximal square problem, there are several common mistakes to watch out for. First, overlooking edge cases can lead to incorrect results. For example, failing to consider scenarios like an empty matrix, a matrix with only one row or column, or matrices filled entirely with zeros or ones can expose weaknesses in your solution. Always validate against these edge cases to ensure robustness. Next, inefficient boundary checks can become a bottleneck. If your implementation repeatedly checks boundaries while expanding squares, you may end up performing redundant calculations. Using pre-computed values or memoization can help optimize this process. Another frequent issue is initializing base cases incorrectly in dynamic programming. For instance, not handling the first row or column separately can cause errors to cascade through your solution. Misinterpreting the problem is another pitfall. Some confuse squares with rectangles, which can lead to incorrect logic. Finally, ignoring space complexity is a common oversight. While focusing on runtime, don't forget that using a full matrix for dynamic programming, when a single row or column could suffice, wastes memory unnecessarily. Always strive for a balanced solution. To succeed in interviews, it's important to fully understand the problem before diving into the solution. Interviewers often test your ability to identify patterns, such as recognizing overlapping subproblems, which are crucial for dynamic programming solutions. Explaining your thought process clearly is just as important as finding the solution. Start by establishing correctness with a brute force approach, then discuss how you can optimize it. Techniques like dynamic programming, prefix sums, or space reduction demonstrate your ability to refine solutions iteratively. Complexity analysis is another key aspect. Be prepared to compare approaches. For example, a naive solution might have an O, n cubed, time complexity, while a dynamic programming approach could improve this to O, n squared. Highlighting these improvements shows your ability to think critically. Communication is paramount, so walk through your approach step by step, explaining how you derive the recurrence relation and handle edge cases. Finally, be ready to adapt to variations of the problem. These might involve finding the largest rectangle, counting all possible rectangles or squares, or handling additional constraints like weighted cells. Preparing for these variations will make you a more versatile problem solver. Understanding related problems can deepen your grasp of the concepts and techniques involved. For instance, LeetCode 221 focuses on finding the largest square in a binary matrix, while LeetCode 85 extends this idea to find the largest rectangle. LeetCode 1277 takes a different angle by requiring you to count all square submatrices filled with ones. LeetCode 363 introduces additional constraints, like finding the maximum sum of a rectangle no larger than a given value. Exploring these problems can help you see the connections between them and refine your approach. Additionally, there are alternative methods to solve the maximal square problem, each with its own trade-offs. The brute force approach, for example, involves checking every possible top left corner and expanding outward to form squares. While this method is straightforward, its O, n cubed, complexity makes it impractical for larger matrices. However, it can be a useful starting point to ensure correctness before optimizing further. Dynamic programming offers a more efficient solution by using a DP matrix where each cell represents the size of the largest square with its bottom right corner at that position. This approach reduces the complexity to O(n) squared in both time and space, making it significantly faster than brute force. However, it does require additional memory for the DP matrix. To address this, space-optimized DP reduces the memory requirement by using only a single row or column, maintaining the O(n) squared time complexity but reducing space to O(n). This approach is more efficient but slightly harder to implement. Another alternative is the prefix sum technique, which pre-computes sums for quick validation of square areas. While this method has an O(n) squared pre-processing cost in O(k) squared per query, it can be particularly useful for problems involving multiple queries. However, for one-off computations, it may not be the most efficient choice. Each approach has its strengths and trade-offs, so understanding when to apply them is key to mastering these types of problems. In this session, we reviewed the maximal square problem and discussed efficient ways to solve it using dynamic programming. Remember the importance of identifying overlapping subproblems in such scenarios. Thanks for watching, and be sure to like, share, and subscribe for more coding tutorials and insights. Until next time, keep practicing and happy coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!